Welcome everyone to this week Autonomy Talks. This week is a great pleasure to have with us Professor David Fridovich-Keil, who is an assistant professor at the University of Texas at Austin. Something about David, so he completed his PhD at UC Berkeley, working with Claire Tomlin. He then moved a few miles away to get to work on his postdoc with Max Schwager at Stanford University. His research goes from optimal control, dynamic game theory, and learning for control to robot safety. And while in the past he has worked on problems in distributed control and reinforcement learning, now he's currently investigating the role of dynamic game theory in multi-agent interactive settings with a particular applications to traffic. Today he's going to talk about trajectory games and in particular learning mixed strategies. And this is clearly a very hot topic at the moment, and we are all very interested in this topic. So I'm very excited to hear the talk, and I let you the stage, David.
All right, thanks so much, and thanks so much for having me. Really excited to be here. I feel like, sorry, hold on, I gotta minimize this. I feel like I've kind of been following a lot of work from your group in the last few years, and it's finally, I've sort of met a few of you or through the grapevine, and really excited to be here and kind of meet everyone. So what I figured I would do is talk through some recent work that we've been doing on how to learn to play mixed strategies in trajectory games. So hopefully this is some familiar stuff for many of you, but also some new stuff. But before doing that, what we'll do is kind of I just want to make sure we're all on the same page, and sort of when we think of games, we're all thinking of the same types of things. So there'll be a bit of kind of old but recent stuff to kind of set the stage, and then a bit of new stuff. Okay. When I talk about games, just to kind of set the stage, I'm often thinking about traffic. So things like on the left, every car here has some idea of what it wants to do. Every driver wants to maybe make a lane change, make forward progress, whatever. Those preferences, could be latent, could be explicit in code for an autonomous car, but at the end of the day, they may be in conflict. And so game theory is the language that lets us kind of talk about natural strategies that resolve this conflict. Traffic's not the only application, of course, lots of other ones. So I'm just showing a couple favorites here: routing games and power systems, economics, etc. Okay, so to put this back in a traffic context, and just help us to think about how these tools at the end of the day are going to get applied, at least how I see them getting applied, is sort of following the ideas that are very common in model predictive control. So whenever we put a control scheme on a robot, on a car, whatever, what we almost always tend to do is think about a receding horizon sort of scheme, where we have some state estimate of what's going on now, plan into the future for a little while, execute for some short amount of time, and repeat. And I kind of see the algorithms I'll talk about in games in the same light, as giving us a way to solve essentially model predictive control problems, but in the multi-agent setting. Okay. All right. So with that said, the agenda for the day, we'll start off. I want to make sure we're all on the same footing with kind of the mechanics of what dynamic games are, and crucially, what are some of the innovations of the last few years in solution techniques. This will kind of lead us naturally to talk about the recent work that will kind of take up much of the talk, is how do we formulate games with kind of more complicated strategy spaces that kind of allow us to talk about mixed strategies, but also some sort of natural version of pure strategies. So we're going to call these lifted strategy spaces. Okay. All right. Okay. So game theory. The simplest place to start is with static games, right? So in a static game, I'm thinking rock, paper, scissors, great example. In a static game, every player's got an objective. They kind of know what they want, and they have several actions available to them. And when each player, here there's n players, chooses an action, those all naturally lead to a particular outcome of the game. and each player has a particular idea of what they think of that outcome. So I'm expressing that here as just some function j. Okay. Oh, one thing I forgot to say at the beginning, please interrupt whenever with questions. I can't see any of you for some reason, so so sorry about that, but please just interrupt with questions. All right. So this is static games. Static games, really natural way to talk about equilibrium concepts in games. So there's different types of things we could look for in a game that we might call a solution. In this talk, I'll focus on the Nash concept. It's the simplest one. So for those who haven't seen it before, the Nash concept is just saying a point is Nash if no player would unilaterally like to change their strategy. So so we'll see some, maybe subtle implications, but classical implications here. But in any event, there are other equilibrium concepts that much of these ideas also apply for. All right. But what is that? Apologies. Okay, so so static games are great, but in this talk, we're actually going to focus on dynamic games. And these are, that's because most of the time in control theory and robotics and so forth, we're interested in what happens over time. So dynamic games allow us to encode outcomes that depend upon time. And so here I'm just introducing a little bit of notation. There's a state of the game X, time T, that I'm showing as a subscript. This will, I'll just reuse the notation throughout the talk. And in general, any player could care about some arbitrary function of what happened over time and what every player did over time. So X's and U's. But objectives aren't the whole story anymore. So so in a dynamic game, it's also really important to be aware of course, the dynamics of the rules. So nothing crazy or unexpected with this. But I think the subtle thing to bear in mind with dynamic games is that the strategies available to each player really crucially depend upon specifying what each player knows when they have to make a decision. So here, the sort of standard way to express this would be, each player's action at time t is some function of whatever they know, and that's this red question mark. So there's a very nice formal way to express this in terms of sets of game states, but in any event, the information structure of the game is pretty crucial. Okay. So this will be something we dive into just a little bit. And just to kind of make sure we're still grounded in that traffic setting I pointed to at first, I've just drawn a example that I don't know if anybody has seen this before, but from talking with Joel at the beginning, it seems like some of you may have seen this example in a few of my papers, but I like this kind of little T intersection as a nice stand-in for showing some complicated behaviors, but not too complicated so we can understand them. So in this little T intersection, what's happening is there's two cars. One wants to go straight, one wants to make a turn, and there's a pedestrian. And nobody wants to hit each other, but you can kind of vary preferences for collision avoidance. So you can put all of the burden for collision avoidance, for example, on the red car. Anyway, you can kind of play with things, but at the end of the day, to put an example like this within the language of dynamic game theory, we need to define what are the rules, what are the dynamics. So write down, the trigonometry that governs how like a bicycle drives or a car drives. Objectives for different players. Here I've written just a few kind of natural ones. Notice here, I'm not restricting anything to be linear or quadratic or anything like this. They can kind of be arbitrary. We'll end up assuming that they're smooth, but that's about it. And the information structure of the game, I'll always kind of be thinking about two options. One will be state feedback, which is what I've written here. Every player's action depends upon the state. Or we could consider open loop strategies where it just depends upon the time. There's lots of other partial information structures, et cetera, but I'll not focus on those in this talk. Okay. All right, so now that we've kind of got the setting under control, I want to dive into how to solve these. So the starting point to think about efficient solution methods for dynamic games is with optimization. So think about coupled optimization problems. So what I've done here in the right is I've written out the problem faced by some arbitrary player I. What they're doing is they'd like to minimize their objective, JI, by choosing their inputs UI, and of course also making sure that the states follow the dynamics. So, this is looks a little benign at first, but then you realize, oh shoot, actually everything here is coupled between the players because the states, I've kind of written them as though they're decision variables for the ith player, but of course the states are shared by all the players potentially. So that's confusing. And then the other thing that's confusing is every other player's decision variables, the inputs used are also showing up in player i's problems. So these problems are all going to be coupled for all the players. So that's, I guess, the first complication as far as solving these problems go. And it leads us to a couple natural thoughts. So the first thing to think about is you could kind of try to solve for each player's problem in turn and kind of just choose some arbitrary inputs for the other players and fix them to what they wanted to play last time it was their turn, something like that. So this is an old idea. Iterative best response has been around forever, and you can think about like rock paper scissors. So if you try something like this in rock paper scissors, I'll declare, hey, I'm going to play rock right now. My opponent will say, okay, well, you're playing rock, I'm going to play paper. Then it's, it'll be my turn to choose again, and I'll say, you're playing paper, I'll play scissors. And so iterative best response is a very old idea, but it's also, long been, people have known also forever that this doesn't always converge. So this is a really natural thing to think about, but it also kind of starts to lead us to investigate more sophisticated solution concepts or solution methods. Okay. But this does actually work quite well in practice for a lot of games. There's been some great work from folks in your group and followed up by others. I have a friend at Illinois who's also done good work in this area, but showing that in classes of games like where players have symmetric objectives, for example, symmetric collision avoidance preferences, iterative best response will converge. So this is a great algorithm in some contexts, it just doesn't always work. Okay, so how else could we look at solving this? Another, I think, really attractive way to think about solving this is in terms of KKT conditions. So at this point for me, this is kind of a knee-jerk reaction, but depending on how many optimization courses you've been in, this will become a knee-jerk reaction, right? And so anytime you look at an optimization problem like the one on top, just write down the first order optimality conditions, and here I've stacked them all for all the players. And this basically gives a set of nonlinear equations that, when we find inputs that lead them all to evaluate to 0, we find a root. We've satisfied all players' first order conditions. So, hopefully they're all at optimality if this is convex or something like that. So this is kind of another direction one could go for finding a equilibrium of one of these games. Okay. So how would you find a root? Well, we know how to find roots in nonlinear equations pretty well. So Newton-esque methods tend to work all right for this. Depending on the particular structure of the problem and the nonlinearities and non-convexities involved, you might need to use some sort of smooth continuation methods or something like that. But at the end of the day, root finding is pretty well studied. Okay, this is something else to do. I guess one thing just to kind of make sure to point out, I said at first that I'd be focusing on Nash equilibria. That is something that if you converge in an iterative best response scheme, you would find. If you do something like this, just to make sure it's people are aware, you won't necessarily find a Nash point, even a local Nash point for as a root of the system. You'll find something called a quasi-Nash. So that's basically like the equivalent of a saddle point, a critical point for optimization. So here it's just saying every player is at a first order optimal point, but it's they may be at a max, they may be at a saddle, who knows. So you need to check second order conditions. All right. So that's another kind of natural way to think about solving these games, and it ends up kind of having different properties, and you can kind of talk about convergence a little bit more simply than in the iterative best response center. I want to shift gears a little bit and sort of start to present some of the complexities of these solution methods. So to do that, I want to just talk about information for a second. So this is that optimization, coupled optimization problem that I had on the previous slide. And I guess just because of the format, probably I won't actually, well, whatever, we'll just ask it. So if somebody could chime in, like, what information, is this problem encoding? Like when we look at time t, and we're at an optimal, we're at an equilibrium for this problem. We've got a time index set of states, x's, and controls u's. But what information does that correspond to? Like, what information does player I have access to at time t?
Can you hear me?
Yes, now I can.
So I guess that will be the states of all players at the current time t, as well as the actions of all other players.
Yeah. So that. Mm-hmm.
It's not clear to me if this is being done in a receding horizon fashion or in a one shot. So, but yeah, I guess if I am a player computing this, I would need to run this optimization, like put myself into the shoes of everyone and run this optimization.
Yep, that's exactly what you need to do. So, to find a fixed point, to find an equilibrium to this set of coupled problems, excuse me, you would need to have access to, the decision variables you would need to keep track of would be every player's state, every player's input for all time. So this is kind of, I think, leading to maybe the conclusion that you're expressing, which is, well, at time, some arbitrary time t, player I needs to have access to all of that information. But just to maybe play devil's advocate or tease a little bit. So if you restrict it to the one player case, so think about just an optimal control problem, deterministic, one player, we can still write down the same problem. And when you do that, what information characterizes the solution to that problem? In other words, is the solution characterized by a sequence of control inputs? Is it characterized by maps from state to control input? Is it characterized by a map from all the states over time to the control input now? Is there some other kind of weird structure to the solution? So I guess in that light, I think it's maybe easier to see this. But what happens when we solve this problem is we find just sequences of the vector variables x and u, right? So we're not actually solving for strategies that map one to the other. And so this is actually going to end up giving us an open loop information structure. And this is actually, like, I think, to me at least, extremely subtle. It's very unintuitive, but that's what happens here, because that's not what I was, that's not what I learned when I, read my optimal control textbook. It's not something that I got out of that process, and I kind of had to pick up along the way. And I feel like it's a very subtle idea. So I want to dig into this just a little bit. So what I'm talking about here is, like, when I say open loop, I'm thinking that the strategy, the control input that player I gets to apply at time t should only depend upon the time and the initial condition. So it's something that you might be kind of thinking about in model predictive control. It's like, well, I sit here at time 1, I look forward into the future, and I decide, okay, well, for the next 10 seconds, this is exactly what I'll do. And then, so that gives me a sequence of control inputs, the UITs, and then a split second from now, I'll resolve the same problem and get a different sequence of control inputs. But crucially, each time I solve that problem, I don't know, it's not baked into the optimality conditions for the problem that I'm going to solve it again in a split second. So there's, the feedback there is the loop is closed by resolving the problem, not directly within the optimality conditions of the optimal control problem. So compare that to a feedback strategy. So think about like a Riccati recursion in LQR, a dynamic program. When you're solving a dynamic program, you're saying, hey, at time t, the optimal thing to do for one player, for n players, whatever, should depend upon the relevant state at that time. So there's a map between state and time to input, and that's state feedback. So for me, I think natural to think about this in terms of, do you have your eyes open? Are you thinking about planning in the future, knowing you'll get to see things, or do you know that you'll never get to see anything ever again? So feedback and open loop. It's sort of abstract, I think, at this level, but I can make it pretty concrete. So think about this example. So here what I'm showing is just a 2-player game. The dynamics are like cars. So, you can change the heading, heading yaw rate. And player 1 here, starting from the bottom, just wants player 2 to go to the origin. Player 2 just wants to get close to player 1, and neither one wants to apply a lot of input. So this is sort of naturally, a pretty simple control objective structure here. And I've shown 2 solutions. One of these colors is the open loop solution, and one of these colors is the feedback solution. And so to me, this, at least I was very surprised when I saw how different they were. But in feedback, you see that both players want to go to the origin. And the reason this happens is that player 1 knows that player 2 is going to get to see it in the future. So player 1 has an incentive to go to the origin now, because player 2 will see that that's happening and then go to the origin. So player 1 can make himself happy indirectly by influencing player 2. That doesn't happen at all in open loop. In open loop, what happens is player 1 says to himself, well, gee, nothing I do from now on will get observed by player 2, because player 2 only sees the initial condition. So basically, all I should do is apply no input, because I want to apply small control inputs anyway. And so that's why in this case, he started with some initial speed. So player 1 just goes in a straight line. And player 2 knows that player 1 is going to want to do this. So player 2 just essentially tries to converge to player 1. So that's what happens in open loop. And that's the Nash equilibrium. So totally radically different. And I guess the point I'm trying to get at with this is that if we don't kind of understand where information is kind of encoded in our solution method, we could end up finding just a totally wrong solution that's not the one we were trying to encode. So, the danger here is if we're thinking about applying this in a receding horizon model predictive control sort of scheme, and we're always finding the open loop solution when we really actually think that, the other cars do see us and things we do will affect them in the future, we may be finding the wrong solution all the time. And, who cares if we're closing the loop with MPC? If it's always telling us to apply no input, then that's not good. So I guess, this issue, who knows how often that would pop up, but I guess to me, this is kind of indicative that we need to be aware of the problems we're actually solving. Another kind of neat example of this, for me, I saw this come up when I was, working for, actually, coincidentally, the shirt very on the top of the stack today, but when I was interning at Neuro, I remember, we studied lots of problems that had to do with making sure that we, the autonomous car, didn't force another driver to suddenly brake or suddenly accelerate to avoid a collision. So we want it to be polite. So a natural way to encode politeness in a game is to have, in this case, like player 1 care about his original objective, but also how much input player 2 has to apply. So, I've just chosen a norm here for that, but who cares? So if you have, something like this to express politeness, and then actually look at the equivalent first order conditions, this is what happens. And basically you end up taking derivatives of the objective with respect to player one's decision variables. U2 is a decision variable. It doesn't depend upon U1. So, this norm goes away and you're left with the original open loop KKT conditions. So if you have these objectives, the open loop solution won't even care about them. So again, sort of subtle things pop up because of information. In feedback, though, this won't happen. In feedback, there will be a connection between player 2's optimal input at time t+1, the state at time t+1, and the input player 1 applies at time t. So these things become connected. Okay. All right, so feedback, what is it? What is it really? So I think it's almost misleading to characterize it the way I did before, but I did it that way because that's the way it's always characterized. People always talk about feedback in terms of a map between something and something, a state, for example, and input, or output and input. But in the context of games, especially, and optimal control, I think the better way to understand feedback is in terms of time consistency. So what I mean here is the existence of a dynamic programming solution to your problem. So if you think about dynamic programming, basically, you always work your way from the end back to the beginning, the bottom to the top in the tree. And in the game context, what that means is at a particular stage, say stage 1, time 1, you need to make decisions knowing that from time 2 onward, all players will act sort of optimally, right? And that extra requirements is something that was missing in the way that we were writing down optimality conditions before. Okay. So how do you do this? So the first thing, when we're writing down one of these game trees, for example, we need to kind of talk about objectives being time separable. That's a sort of a pretty standard condition. So like a sum over time, a min over time, something like that. And when you actually just write down, the dynamic programming principle of optimality like this, what you see is that to encode kind of Nash conditions or optimality conditions in the future, it's important to express these kind of constraints for future times. So the ones that I boxed here with the descriptors. So the blue one is saying in the future, other players follow the optimal state feedback law derived in the future, and similarly in red, that's what's happening as well. So there's some recursion that needs to happen. This is totally expected when we think about dynamic programming, but it's maybe a little bit unintuitive how to treat these recursions, computationally speaking. Okay. So what's going on? We basically defined optimal strategies for all the players recursively. So in terms of the future optimal strategies, and there's big T time steps here. So there's T levels of nesting, which is probably starting to sound a little bit horrible. So numerically speaking, it is horrible, because it means that before we were able to just write down first order conditions for everybody, call it a root finding problem. How would we solve root finding problems? We'd start taking first and second derivatives, use Newton's method or some variant of it, and we'd be happy. But here the problem is, if we try to do that, we need to differentiate through all of these layers, unpeel the onion, and now we're gonna have to start taking god-awful derivatives, basically. So this is kind of the source of some problems. All right, so that's hard to do. What we've done in the last few years is show that basically you can neglect high order derivatives, or anything bigger than 1, basically treat optimal strategies as affine, and at least this is computationally tractable. What we've also shown is kind of how to relate this to kind of the optimal policies that would arise without that approximation. So it's quite difficult to actually get some hard bound on suboptimality, for example. So to talk about does this lead to an epsilon local Nash, for example? It's difficult, and we have not been able to show that. But basically, this is kind of how to understand this computational approximation in the context of the problem that it's trying to solve. So at the end of the day, when you do this and sort of mix in a few kind of details from optimization, what you get is an algorithm that looks very simple. Basically boils down to something like repeatedly solving linear quadratic games. And yeah, so that's essentially what it boils down to. Each linear quadratic game can be solved really efficiently. It's a Riccati recursion. Something I guess also to point out is just like we were talking about open loop and feedback solutions, those solution concepts also make sense in linear quadratic games. So here it would be important to find the feedback solution to the LQ game. If we found the open loop solution, we'd recover the open loop local Nash equilibrium, and we could prove that it would be actually be local Nash, not even epsilon Nash. So so the feedback condition here is actually quite important. Okay, this works quite reliably. So here's just a little Monte Carlo example to kind of give us a bit of intuition. So here I'm showing 3 players in a hallway. None of them want to get too close to the others. Nobody wants to hit the walls, and they all want to cross. So what I did is just seed the solver with a whole bunch of random initial strategies for the players, and then just run the convergence for each seed and cluster the results. And what you see is that they cluster really nicely. So basically recover the natural kind of at least intuitive equilibria that you'd expect to see, having since we've all been in this situation, I'm sure. So we see that on the top, the first cluster, the green player just kind of stays in the middle, and the other players kind of slow down and hug the walls, give them room. And then the other 2 clusters, the middle and edge players interchange places. So this type of method can, at least recover the equilibria we'd expect in this type of problem. And we've tested lots of other kind of, I'd say, contrived examples like this that are simple and have expected equilibrium structure. And we've also tested it in hardware. This is kind of the most fun I've had in hardware testing, but to actually put this on aircraft. Unfortunately, they wouldn't let us fly it at this stage. And I understand that flights have happened, but I've been graduated since then, so I don't know how they went. But in this case, what we were trying to do was taxi around the airport and avoid kind of random taxiway intruders and sort of pose those intruders as kind of collision avoidance games and so forth. But all this would run easily in real time for those types of problems. Okay, so the point that I wanted to convey with all of this discussion of solution methods is just to say that, hey, when we look at multi-agent interactions, it's good to think about them as games that are played over time. Those games, have a lot of subtlety to them in terms of I focused on information, but there are other subtleties, solution concepts, etc. And what I showed was how to find kind of approximate local Nash solutions in real time. Okay, so let me pause here and take any any questions, just focusing on things that I've already talked about, and then I want to transition to talk about some new work that kind of builds upon kind of some open questions.
I have a question.
Shoot.
Isn't the open loop strategy, shouldn't it coincide with the feedback strategy on the optimal path? I struggle to appreciate really the difference. To me, the difference would arise only if there's like disturbance or something.
Yeah, so that's really excellent. Yeah, this is a really excellent intuition. So, so in the single player setting, this setting. So if you think about one player, and everything is deterministic and there's no disturbances or anything like this, then you're 100% right. So think about an LQR problem. You can solve an LQR problem with a Riccati recursion. That'll give you a feedback policy. And you can then unroll that feedback policy from time 1 to time t and get a path. That path will exactly coincide with what you would find if you instead posed the problem this way. It'd be a quadratic program, and you plugged it into your favorite QP solver and looked at the trajectory that would arise. It'd be the same solution. Now, that's not going to happen anymore when there's either like a stochastic disturbance, or there's another player or something else that basically makes it so that the decision maker, in this case, let's say player I, can't know exactly what the state of the game is based upon the initial condition and knowing what he did up until now. So if there's anything that breaks that, equivalence, then there becomes a difference between feedback and open loop. And that's exactly what's happening in the game case here. So here there's another player, and the actions of the other player are not observed. So the actions of the other player can perturb the state of the game. And if a particular player doesn't see the state at time t, then they have no way to know what the other player did.
But in the coupled optimization,
Mm-hmm.
the open loop one, so
Mm-hmm.
the sequences of the sequence of inputs of both players and states should be optimal on that path still, right?
Yeah. So
it should still coincide with the closed loop, except if there's a disturbance.
Yeah. So this is why it's a little bit, not a little bit. It's very confusing, I think, when we think about feedback in terms of maps, only maps from state to input. Of course, I can write down a map in that type of map that just returns a particular input at a particular time, no matter what the state is. So you can always reconstruct a feedback strategy that, the proper term would be represents a open loop strategy. And likewise, you can say, if all of the other players are playing an open loop and I know their strategies, then I would also be happy playing an open loop, even if I have feedback strategies available to me. So thinking about just the map is, it's part of the story, but the real story, I think, at least the way that I like to understand it, I think it ought to be understood, is in terms of dynamic programming. So in terms of time consistency. So if you think about feedback, it's not just any state feedback map that constitutes a feedback equilibrium. It's a particular one that's restricted to be time consistent. Does that make sense?
I have to wrap my head around it.
Okay, yeah, it's a very subtle concept that it's one of those things that I would open up this book, this guy, like, random times throughout my postdoc, and just be like, okay, well, I'm learning something new today. And anyway, I read it. God knows how many times I've read that book. So it's a great book. Highly recommend. Any other questions? All right. So let me start to speed up just for the sake of time, but I want to just kind of give a little bit of a vignette of some recent work that kind of builds upon I'd say a pretty gaping hole in what I've talked about so far. And that's the kind of question of existence. So, when we think about rock, paper, scissors, pretty easy to convince ourselves that kind of deterministic or pure equilibria don't exist. So, so here, you would never just tell me, hey, I'm definitely going to play rock. Like that would, I can definitely exploit that choice. So, there's not going to be a pure equilibrium in this problem. Likewise, in these kind of trajectory games that we think about maybe in the traffic setting, or here I'm showing a pursuit evasion game, there may not be a pure solution to deterministic Nash equilibrium. So here I'm showing just some candidate equilibrium, which you can see is just eventually the pursuer catches the evader. Probably ought to be able to convince yourself that this is likely not a Nash point, because the evader can probably do something to do better than getting caught if the pursuer is fixing their strategy. So, excuse me. So, pure Nash might not exist. And the thing that we do know, though, is that mixed Nash always exists as long as the kind of action space is finite. So I'm thinking here about static games, but go back to rock, paper, scissors. Classically, right, the mixed Nash solution to this game is every player just flipping a coin and uniformly at random choosing. So so the same is probably also true in trajectory games, or static versions of trajectory games. So here's some recent work from over at ETH, and I know there's several other papers that have kind of used similar concepts in recent years. But the basic idea that I think was I guess pioneered here, and I think is a really great idea, is to say, well, let's look at a particular problem of interest. So here it was racing, and talk about a finite number of kind of fixed primitives that each, in this case, car, gets to think about. So here on the top, they're showing 3, and on the bottom they're showing many random choices, and then just play a finite matrix game among these options, and find there's guaranteed to be a mixed Nash equilibrium in that setting. So existence is solved for us. I guess there's a couple of kind of interesting points to bring up here. The first one is, to me at least, is really attractive, because the primitives can be computed in parallel, right? Each one is just a trajectory that is probably parameterized somehow, or chosen by some heuristic perhaps. But at the end of the day, it's something that can be kind of computed in a independent fashion from every other primitive probably. So that's attractive computationally. And then the other kind of nice thing is that it's, I'm putting this in quotes, but it's global, meaning that if you could really sample the entire space of trajectories densely, and then find a mixed Nash solution, then that's probably the best you could ever hope to do. That would be like capturing all of the intricate global structure of, in this case, the racetrack, and the dynamics of the other players and whatever. So this is not going to suffer any kind of local properties like the gradient-based methods we saw before. So so those are really attractive properties, I think. And I'd say the only slight pain point here is that this requires us to either have a few very strong kind of heuristically chosen candidate trajectories. So maybe turning left, going straight, going right, like on top, or not having access to that information, or not choosing to use it, and just sampling a bunch of random, potentially weak guesses. So that's what's happening on the bottom. And in either case, there's kind of a little bit of pain, right? In the first case on top, you'd really need to have access to kind of expert information. On the bottom, the more trajectories we're sampling, the harder computationally that is. And even if they can be computed in parallel, solving the resulting finite game is maybe not going to be so easy. Okay. Just to kind of ground this a little bit, as this video is playing, the story here is the work that I'm sort of presenting in this little vignette did with a couple co-authors. One of them is Forrest Lane on the bottom right there, and Forrest actually created this little simulation as a part of a programming assignment for his graduate class on game theory at Vanderbilt last semester, and so this kind of started us to think about if these, in this case, pursuit evasion game, if the pursuer and the evader are playing this game, is there anything interesting that they can learn? And so here, the way that the assignment worked was each player planned, motion primitives, trajectory primitives to each of these stars along the outside of the arena. And then, so that defined however many trajectory candidates at each point in the space. And then they solved a matrix game and played for a few steps. So I guess the question we started to ask was, instead of just picking these things either at random or with some heuristics like Forrest did in his class assignment, couldn't we maybe try to figure out how to learn strong trajectories, a few strong trajectories, while knowing that they're going to be used to play a matrix game at the end of the day? So can we kind of learn the primitives, the pure strategy options, while knowing that we're going to eventually pick a mixed strategy? So this is this idea of lifted strategies that kind of underlies this work. It's pretty hot off the press. So I guess if anyone's coming to RSS this year, you'll see the full story there. But the basic idea of how we do this is to as others have done, represent trajectories parametrically, and then train. In this case, we trained a neural network, but actually that's kind of mostly an kind of online optimization idea. It's not strictly necessary, but try to figure out how to generate these parameters of these trajectories based upon current game state, and then solve the resulting bimatrix game for a mixed Nash. And so these are the kind of main operations, and we need to figure out how to do these efficiently and differentiably, crucially, to be able to learn in this type of setting. So to kind of pin this down, here's a computation graph of all of the kind of important operations that are going to get performed here. So there's initial conditions on the left, so x1, x2 for two players that I'm showing. There's some maps that are parametrized to go between the initial conditions and parameters of the trajectories. There's a function which maps the parameters into the actual trajectory candidates. Each player has a particular objective that hopefully is smooth, that yields kind of matrices that define a bimatrix game in this case. Given a bimatrix game, there's great algorithms out there to find mixed Nash solutions to those games, and that gives us a value of each player's objective at Nash. So what we're going to do is basically do all of those operations forward, parallelizing whenever possible, etc. So that's actually going to be quite efficient. And the kind of main contributions of the paper are actually showing how we can go backwards, how we can differentiate and propagate derivatives backwards from the game values on the right back to the parameters of these trajectory generators that we call them on the left, those pre-trained boxes. So if we can do this efficiently, then we can train these things offline and then actually solve these games online. So that's how that works. There's really two crucial steps that I'll focus on briefly, and then just kind of show you a few results. So the first thing we need to be able to do is make sure that we can differentiate through the map between parameters of trajectories and trajectories themselves. This is a problem that's been essentially quite well studied in recent years. So I'm just showing, I think, probably the most cited paper on this. But for those who haven't seen this work in differentiable optimization, basically it's I'd say generalizing some really kind of important ideas that we probably all saw in high school calculus to the setting of optimization problems. So what you do is think about parametrizing, expressing the parameters of the variables you care about. So in this case, parametrizing the trajectories by variables that enter into an optimization problem. So here, these variables C are entering into the objective of an optimization problem, and there's constraints in the problem. So this is nice because it lets us kind of make sure we're respecting dynamic feasibility, et cetera. And so the way that you differentiate implicitly through this is you write down the optimality conditions, and then express the derivative of tau with respect to C implicitly through that map. there's good ways to do this. There's some subtleties that we had to, I'd say, work through to make sure that this was effective in our context. I'm happy to talk about them, but for the sake of time, I think I'll skip them right now. Yeah, so we can talk about those if there are questions. And I'd say the kind of one of the key contributions that we had was to show that you can also do this in the setting of games. So in the bimatrix context, which is what we were handling, the Nash problem results is expressed as a linear complementarity program. So when we kind of write out what the complementarity conditions are in that program, think carefully about whether strict complementarity holds or not. We can also implicitly differentiate through that map. Okay. I want to make sure to focus a little bit on what is this actually bias? So I'm going to just study the pursuit evasion game. I know it's a very toy example, but I'll show some extensions at the end. In the pursuit evasion context, this is the problem that we're trying to solve. Pursuer is trying to optimize two trajectory candidates. Evaders trying to optimize two. They're going to eventually choose mixing weights according to a bimatrix game played among these two trajectory candidates per player. So the problem is expressed on right, but there's a couple of really interesting things that arise. The first thing is that we can show just from extensive Monte Carlo simulations that what happens is when you're learning even just two primitives, it really outperforms this kind of random sampling that we saw in the racing context before. So, it's a different example, and take from that what you will, but the point I think is fairly intuitive, that if players are allowed to refine their trajectory candidates by learning in this manner, they can choose ones that are efficient. So here what I'm showing is just game value with respect to number of randomly sampled trajectories. So in our case, we just learned two. That's why we're kind of just a constant here. There's some uncertainty coming from the Monte Carlo sampling of just trying this a bunch of times for different initial conditions. And then the gray is showing what happens when we play with random samples. Okay, so basically learning really is pretty efficient. Kind of another thing that we can test is actually, do the trajectory candidates we find, are they pure Nash? And so here we have to find a setting where there exists a pure solution, of course, but what we see is that actually we converge to very reliably different game values, which tells us pretty clearly that these candidates are not pure Nash. So we're finding different solutions. That should have been hopefully pretty intuitive from the picture, that neither of these pure candidates, pure trajectory candidates for either player are going to be in a pure Nash with one another. So we're changing the solution here. Another thing to mention is that we can train the trajectory generators really efficiently online, because everything is parallelizable and differentiable. So here, I think forward passes, we clocked them at something like 2 milliseconds, just a handful of milliseconds on a standard, my laptop kind of thing. And then backward passes were, I think, around 20 milliseconds, not too bad. So we can learn pretty efficiently, and I think this is going to speed up soon. Yeah. And you can see after, in this case, I think a couple thousand gradient steps, that's the turn on the top, we've kind of learned pretty competitive looking behaviors of players choosing to mix and juke each other out and so forth. And then the last thing we tested is kind of constructing a bit of a metagame. So here, allowing players to choose to play either with lifted strategies, the ones that we've introduced, or pure strategies, just one trajectory candidate each, and solve these games separately, and then pit them head to head. And we see that very reliably, players prefer to play with lifted strategies. So if you think about this from the evader's perspective, they would always prefer to randomize, because this gives them, this basically breaks the pursuer's ability to exploit their decisions. And then we also experimentally show that when the evader is playing with lifted strategies, the pursuer prefers lifted strategies as well. So that's what's happening there. And then the last thing to say is that none of this analysis, none of these tools are limited to the two-player setting. So we've been recently trying to build these up in the n-player context. There's a few difficulties. It's no longer a bi-matrix game, so we need to be much more careful with how to solve the n-player finite games and propagate derivative information implicitly. So we can do that quite well. And then there's also kind of some nice AD speed ups. So for those who are kind of like to go deep into some of these tools, before working on this, I was not aware that you could mix forward and reverse mode autodiff. So that's pretty fun. And some of these kind of operations in our computation graph are sort of more efficient to do in one mode with respect to the other. So there's some nice basically nice optimizations that we can throw in to make this work quite efficiently in the n-player case. So here's just, kind of some cooked up example of multiple agents trying to avoid one another, but get to the goals that we've given them. Okay. So that's all I've got. The takeaway message, I guess, from this vignette that I want to drive home is just that, pure Nash solutions don't always exist. So the efficient solution methods we saw in the first half of the talk, they're great when solutions exist, but they find local solutions and they don't always work because the solutions aren't always there. But mixed solutions do always exist in the finite kind of action spaces. So what we've shown here in this recent work is that you can kind of blend ideas of solving for pure strategies with solving for mixed strategies and kind of learn to do this efficiently. So that's all I've got. I'd love to take questions as time allows. I can stick around and thanks so much.
Thank you, David, for the nice talk. Let's open the stage for questions. You can either write in the chat or unmute yourself and ask directly. No one wants to break the ice? Maybe I can go ahead. I think the last part of the talk, I found the last part of the talk interesting. I was interested into how are you thinking about generalizing these to other scenarios or other kinds of games, like maybe even the first kind of games you were talking about, in which you have these intersections or junctions.
Yeah, I think it can totally be generalized there. So one thing that we've been thinking about and have some sort of preliminary results, but I thought they were a little too half-baked to show in this talk. But we can totally think about solving, basically trying to identify a like an approximate value function, for example, for players, so we can try to solve this, find feedback solutions to these games. And I think those would be quite relevant in all kinds of traffic scenarios. But also, even without that, I think that there's pretty natural ways to think about these in sort of other general sum contexts. So that the kind of n-player collision avoidance thing at the end, that's a general sum game. The pursuit evasion game was a zero-sum game. So I think there are kind of really subtle things that do happen. So one thing, for example, is that depending on the game, you may not have a meaningful mixed solution that comes up, right? There may be a pure solution, it just doesn't always exist. So something that's totally true in, for example, the potential games that I mentioned before, where players have kind of compatible collision avoidance penalties, there will exist a Purenash, at least locally. So in those games, there's probably not much point for these lifted strategies, but we're kind of trying to get a better handle on that.
Okay, thank you. Interesting. Any other question? Okay, that means either everybody's still thinking about things, or so maybe a question which is a bit biased, since before the talk we talked about different ways to handle the kind of constraints of your problem. In the first part of the talk, you were mentioning these ways into how to include politeness or other metrics into your scalar metric. But then before the talk started, you actually mentioned you're thinking about including more general preference structures, like maybe the ones we proposed.
Yeah.
Can you elaborate more on that, or is it too preliminary as a thought?
No. I'd love to elaborate. It's like I have not thought about it very deeply, and I'd love to get input from anywhere, and just throw ideas around. Okay, I guess to start, I haven't really thought too hard about how to do it in the for these kind of local Newton-esque methods, iterative LQ sorts of things. I think the difficulty there is, I guess, I don't have a clear sense of how to handle it seems like there's kind of some non-smoothness going on with deciding which preferences are kind of active at which times. In other words, do you care about collision now, or does collision not matter? At this, like locally speaking, is collision not a concern, and should I instead care about some other constraints? So I think about those in terms of like active set methods. I want to think about those in terms of constraints being active or not active, and if we can kind of think about them like if we can kind of if we can express them as sort of like a working set of potentially active constraints, then I think there's very natural ways to apply all of the kind of computational tooling from the first half of the talk. So I didn't show it in here, but we've totally handled kind of, I guess, standard kind of general feedback Nash equilibrium problems. So like if we have a non-collision constraint, not a cost, but a constraint that's maintained by one player or the other or both, can totally assign Lagrange multipliers to those constraints and treat them with either an active set method or an interior point method or something like that. But in the kind of hierarchical constraints or ordered constraints setting, I'm not entirely sure how I would go about doing that, but I feel like it should be very possible. So that's, I guess, what I was going to say there. And the other thought I had is kind of going to the stuff I talked about at the end with this kind of notion of lifting. I think that that's probably also somewhat reasonable in that if you look at a particular choice of trajectory primitives, it's probably reasonable to evaluate, okay, like which constraints are active right now, which ones should these primitives be caring about, and differentiate implicitly through them, basically bake them into the trajectory parameterization here.
So essentially the second part boils down to estimating the types of the players. If you think about hierarchies of preferences like this, estimate the hierarchy of the player. Exactly,
yeah. And I don't know how feasible that would be. Like everything that I've shown is kind of like, I guess, think about it as like model predictive control that's going on in one player's head, and they're making conjectures about what other players want to do. So I'm not sure how feasible it really is to think about one player conjecturing that the other player has, a particular partially ordered set of constraints or something like that. I haven't really thought about that, but if you could do that, I think that'd be how to approach it.
Very nice. Yeah, we'll talk more at ICRA about
I'd love
this.
to.
Any other questions? Seems today we have a silent audience, but that's okay. I think you gave your contacts in case people want to reach out.
Yeah, please do anytime. Yeah.
And thank you again very much, David, for the great talk, and good luck for the next steps.
All right. Thanks. Great to meet you finally, and look forward to it.
Thank you.
Yeah.
Have a good one,
Yeah.
and thank you all for participating. See you all next week for the next Autonomy Talk.
Bye-bye.
Bye.